Now, what if instead of a resistor, we decided to combine an inductor with a capacitor? This is called an LC circuit, and we get some behavior out of it that's a little bit surprising. If you look on the far left, we have a charged up capacitor, and we connect an inductor across its terminals. Well, the charges see a way to get to each other, so again, in our physics conventional current sense, we assume the positive ones want to race around the circuit counterclockwise. In reality, it's electrons going clockwise, but anyway, we get a current established like this, our conventional current. The inductor does not want that to happen, so it fights the establishment of this current, and it takes a little while for that current to build up. So you can see here we start with maximum charge and zero current, and as the charge starts to drain away, the current builds up. It's carrying these charges around from top to bottom, and eventually we get to the point where the capacitor is completely discharged. However, now the inductor doesn't want to let that current go, so it won't let that current die, and that current is taking positives from the top plate and moving them to the bottom plate. Now what's going to happen if the current keeps going? We're going to charge up that capacitor in the other direction. So eventually we get to the point where the inductor lets the current die off, but by this point we've charged up the capacitor opposite to the way we started with. Now what happens? Well, now we have a capacitor charged up as before, only the other way, connected by an inductor. So we start getting a current back this way. We start draining positive charges off the bottom and moving them around to the top. And you can see here we have these sine curves or cosine curves. We get this infinite oscillation between energy stored in the capacitor as charge or in the inductor as current. And we just go back and forth between them. This is like like the roller coaster problem. We go back and forth between potential and kinetic energy over and over again. This setup is called a tank circuit, and it's used in radio reception. Um, in reality, of course, we would have some resistance, just like in reality our roller coaster would have some friction. But this thing is acting like a mass on a spring on a frictionless table. It's acting like a simple harmonic oscillator. If we move that mass, it goes back and forth forever. Once we start this, it goes back and forth forever. If we put in Kirchhoff's voltage loop equation here, it would be L di dt plus Q over C, because that's the voltage on the capacitor, equals 0. However, we can write di dt as second derivative of Q with respect to time, and we get this. This is the harmonic oscillator equation. Again, you're not supposed to know how to solve differential equations, but if it's one you've seen before, you can recognize it. It just says the second derivative of this function is proportional to the negative of itself. That's what we've got here. This is what we got for the mass and spring case, where we had F equals negative kx, and that was set equal to ma. Again, a math person would say this equation and this equation are exactly the same. All you're doing is changing the letters. So we could copy the solution from last semester directly. We have this charge as a function of time is q0 cosine omega t plus phi. The frequency omega we get from the square root of this, not the negative sign, but 1 over the square root of LC. That's our omega. And Q0 is the maximum charge on the capacitor, so it's what we started with. Phi is a phase constant, just like it was last semester, and it essentially tells us where did we set our zero of time in this oscillating cycle. Here, this says the charge and current will just oscillate back and forth forever. If we wanted to find the energy of this system, we could say, as we did with the mass and spring, the total energy is kinetic plus potential. We could write potential a couple of different ways. Since we know Q is a function of time, finding I as a function of time just means we take the derivative. So we do that, and we get this. Negative omega Q naught sine omega t plus phi. This works just like the kinetic energy and potential energy in the mass spring case, where we say if we add them at any instant, it's equal to the maximum kinetic energy or the maximum potential energy. So this would be the mass and spring. We got all this last semester. Now, just like a frictionless table isn't realistic, a system that has no resistance, it's just inductance and capacitance, is also not realistic. We're going to be using regular wire for the coil and the inductor, the leads on the capacitor, the connection between them, so there will be some resistance in our system, and that changes our problem. This is now an RLC circuit since we have all three things. In the upper level circuits class, what we would learn is you can treat generators as batteries with complex values and inductors and capacitors as resistors with complex values. So then we could use all the tricks we learn and you would learn in the upper level class to solve resistor and battery circuit combinations. You could apply them all to this. You could, of course, do the math since complex numbers aren't really that complex anymore after you've had the math that you've already had. But it's a little bit more specialized than we want to do in the introductory course. So what we're going to do is concentrate only on series RLC circuits because these don't require us to use complex numbers. Now from this, Kirchhoff's law gives us L di dt plus IR plus Q over C equals 0. This is a differential equation where we've got Q, its first derivative, and its second derivative. This looks like the problem from last semester of the mass on a spring connected to a shock absorber. This is also called a damper or a dash pot, is really old terminology for it. We had a velocity-dependent resisting force then, F equals negative BV. We get the same answer here that we got last semester if we just change our variables. Our omega prime is square root of 1 over LC minus r over 2l squared. This is an exponentially decaying sine wave, and it looks like this. Here's our charge, and then the green dotted line is sometimes called the envelope that the cosine function lives inside. Now, there's an interesting question here, and I'm not going to give you the answer. I'm going to let you figure it out, or you can ask me in class. We started off with charge Q naught here, and we see it oscillating, and it eventually goes off to 0. And what I want to know is, what happened to conservation of charge? If we started off with this charged capacitor, and we had Qt equals Q0, so T equals 0, and this is 1, this is 1. So at T equals 0, we have that charge. If I wait several time constants, I get Q of T equals 0 instead of Q0. What happened to conservation of charge? Think about that. Now, last semester, all we saw with the damped simple harmonic oscillator can be transferred over to this. There's the concept of a resonant frequency where we have omega if there's no resistance or omega prime if there is. And that's why we use the LC circuit as a radio tuner. We can have resonance, and instead of shattering a wine glass, we have a radio tuner. Usually what you would do is you'd have a fixed value of L and an adjustable capacitor. Changing that resonant frequency tunes the radio for you. Now we can set up a correspondence between our two models. The dynamical variables we cared about last semester were position, velocity, and acceleration. This semester it's charge, current, and dIdt. There's not a nice name for dIdt that I'm aware of. We can match them up in this table below, and each one of them is paired with a value of our components. That when we sum the forces in the mechanical problem, for example, X and K are paired together for that spring force. V and B are paired together for the damping force, and M and A are paired together because of Newton's second law. We can then find the things that we pair with our Q, I, and dIdt. We pair Q with 1 over C because Q over C is the voltage on the capacitor. I we pair with R because IR is the voltage across the resistor, and L dIdt is the voltage across the inductor. So here all of these things were forces, right? Kx, Bv, Ma. These things are all voltages. What else could we call them except voltage that would sound a little bit more analogous to what we've done? We could call them electromagnetic forces. So this is why we one of the reasons we have this electromagnetic force, even though it is in no way a force, and it seemed ridiculous at the time, we can see that it's essentially the electromagnetic equivalent of force. So hopefully that makes you hate it a little bit less now.